Good morning, class. So if you remember, the last quiz problem is to find out the sampling frequency. Sampling frequency should be greater or equal to twice the maximum frequency in the original signal. So today, let me do an extended example from that problem. So here is the problem that we had last time, the quiz problem that we finished the number one. What is the minimum sampling frequency with no aliasing if the signal in the frequency domain looks like this? So we have here the signal is the frequency domain has component from 1 kilohertz to 9 kilohertz. The maximum frequency is 9 kilohertz. Therefore, the quiz problem is very simple. The sampling frequency should be twice the maximum frequency, so that's 18 hertz. Now, today I'm doing a little extension, and the problem number 2 is, what is the minimum sampling frequency with no overlap occurs in the frequency range of 2 to 8 kilohertz? Suppose this is 2 hertz and that is 8 hertz. All I care about is the signal within this range from 2 to 8. And I want to make sure that there's no overlapping over this range. So to do this problem, we really need to understand what does this folding effect do? How is it related with the sampling frequency Fs? So if I want to have something that has no overlap within 2 and 8, we know if we do anything of discretization in the time domain, that will give me a periodic copy of this entire frequency from here to here, negative to positive. So I can somehow fold this frequency component to here. And another one is there. So this is just move the entire baseband signal, or the to sampling frequency will be here. This is my Fs. This is the minimum I can get without any overlapping of this range, without any overlapping of the range from 2 kilohertz to 8 kilohertz. Right? And then I know Fs should be twice the middle point, which is here. This middle point is 8.5. Therefore, to answer this question is I say a sampling frequency Fs equal to 17 kilohertz, 2 times 8.5. 17 kilohertz will be sufficient in order to not to have any overlap occurs in this frequency range. Okay, so this is just a way to give us a better understanding how the sampling frequency works. It's just to fold this part. In this case, for this part from here to here, and make it here, make it to Fs. Now let's get back to the chapter on signal and a system. We talk about the basic signals. We talk about a discrete system. System can be identified by an impulse response H. And we talk about system. You have a transformation or the operation, make a signal X to a signal Y. There are some of different properties or features of different systems. Last time we were talking about the linear systems, time-invariant systems, what is causal system, what is a stable system. Okay, today let's continue with interconnections of discrete time systems. 2 systems here using operation 1, T1, and operation 2, T2, to indicate that. 2 discrete time systems can be cascade. Cascade looks like in this block diagram. So I have input signal Xn coming to the first system T1, becomes signal Y1, and then goes through the second system called indicated by T2, and then become Yn. So we have if in the cascade operator indication, the expression can be seen as yn equal to xn with a operator t1 and then has operator t2. Then the combined or the cascade operator, cascade system is t2, t1. In general, t2, t1 is not equal to t1, t2. That means in general, I cannot change the order of t2 and t1, 2 operators. The only time I can do this, the only time I can do t2, t1 equals to t1, t2 is when I have a linear time-invariant system. If I have a linear time-invariant system, I can swamp the order of those two building blocks. So T2 is here, and then I have a transpose T1 here. Okay. So that's a cascade of two systems. Parallel is similar. It's easy to understand. So I have an input signal xn going through the first operator, xn going through the second operator. The output is combined. Therefore, the parallel operator can be written as T1 plus T2. The block diagram showing at the bottom. So we have seen different types of systems, different type of linear time-invariant system. What are their features? Now, how to analyze a linear time-invariant system? So here, let's move to the next part, which is an analysis. In general, a linear time-invariant system can be described by an input-output relation. So the input is xn going through my system. It's linear time-invariant. We know that the linear time-invariant system can be indicated by Hn, which is the impulse response, by Yn. Okay. Hn is the impulse response. I can get the system using this block diagram. We can also use a general convolution to represent system. We will see that using a convolution to represent that. So that's input signal xn convolved with the impulse response. Okay, we will see that. So in general, what we do is we have the input signal x, and we have the output. This is my current output at time n. So the current output is a linear combination of all these inputs. This is a linear combination. So k is from 0 to m. Let's say in this case, k from 0 to m, and that is a causal system. It does not depend on future inputs. It depends on xn minus 1. K can be 1, k is 2, xn minus 2, and all the way to a finite amount of those inputs. So in this case, xn minus capital M, finite amount of input. And then b sub k is just a weight, so you're adding all these together. However, I have another term here. This term is a feedback term. So I have all these previous output y, which is yn minus 1, k from 1 to n, yn minus 2, and I have a finite amount of this memory, or the previous output, all the way to yn minus capital N. Then weighted by a sub k, add them together, and that is the feedback term. Now, conventionally, we put a negative sign here. It's because if you move the entire term, the first term, to the left of the equation, so you have all the y's adding together equals to all the x's adding together. And the y, we can think of A0, which is the weight or the parameters on this current yn. A0 is always equal to 1. Okay, so we have all the parameters of y on the left and everything of x on the right. This is a difference equation. It is a difference equation, and it is a linear equation. And because I only have all the signal input and output with their delayed version, there is no x squared, there is no cosine y, or any like those. So it's a linear, it's a difference equation, and then it's a linear equation. Looking into the details of a linear time-invariant system. So we use this expression where x sub k are the elementary signal component. We use that to decompose my signal, any signal, decompose into a sum of those elementary signals. Now, we know there are a few of those so-called elementary signal components. Two of those we used quite often. One is the delta function, which is delta n subtract k. So this is just a delta function that has valid value at time n equals to k. We know we can use that as an elementary signal component. We can also use another elementary signal, which is e to the j 2 pi fk n. Okay. This is an exponential function. So you can think that as a delta function in the frequency domain. I only have a valid non-zero spike at frequency f sub k. And n is an integer. So I have the spikes at n f sub k. And that can be another elementary signal components that can compose my original signal xn, any arbitrary signal xn. All right, suppose that I have a linear time-invariant system, the operation indicated by t. For input signal x, through the operator, I have the output signal of y. Therefore, we have yn equals to the transformation or the operation on xn, because xn now can be written as the sum of these elementary signals. And we said this transformation or this operation is linear time invariant. It's linear. It's linear. Therefore, I can put the summation out of this operation. Then operation is working on each individual inputs, x sub k. C sub k is a constant weight, so I can also pull that out of my operation. It's a linear system. Therefore, I have this term, and then each one of those operations that give me a separated output, which is y sub k. So the output can also be separated as a sum of all these individual output. Each of those output is result from an individual input elementary components. And then we are using the same weight, C sub k, to add them together. So this is quite easy to understand. It's a linear system. So we have this superpositioning law can do that. For example, we are using x sub k equals to e to the power j omega k n. K is 0, 1, 2, all the way to n minus 1. Where here, this omega k is 2 pi k over capital N. Omega k are the harmonically related. These are harmonically related, which means I have all these frequencies, they are equally spaced in the frequency domain, where 2 pi over n is fundamental frequency. So in the frequency domain from 0, and I have a frequency at 2 pi over n. This is my omega 1. Omega 0 is at 0. I have another spike here at 2 pi times 2. When k equals to 2 over n. This is omega 2. And then we have all these equally spaced frequency spikes. We call that we have a 0 here. We call those harmonically related. And then all the way to 2 pi times n minus 1 divided by n. This is my omega n minus 1. Now, if I go beyond one space here, and then there it becomes 2 pi n over n, that is just 2 pi, it will have the same effect as this 0, right? So indeed, I have in this case, I have a period from 0 to n minus 1, k equal to n minus 1. We will see that later on. So it's a discrete time signal. Once it's a periodic, I will have discretized in the frequency. I also have a repetition, the periodicity in the frequency. But this is one way of choosing the elementary signal. Later we know that is a Fourier transform. This is a discrete Fourier transform. Let's choose the first elementary signal, which is the delta. It's simpler. So that's another way we can decompose the input signal. We just simply choose this as a delta function. So the signal xn, if you multiply by delta and subtract k, we call that a sifting, which is that we pick up the signal when at a time n equal to k. At any other time, it's 0. We only need x of k. This value can be selected because of delta function. So it's the same as xk times delta n minus k. Therefore, my input signal xn, it can be decomposed as a sum of these delta functions. Those delta functions are centered at different time of k. And the entire thing can be written in this format, xk. I just simply pick up each samples multiplied by this delta n minus k, sum of together. That's my signal xn. And this part is my signal components. Those are the x sub k's. So it's very clear to see on a picture what we have here. This is xn. Xn is discrete time signals. So we have a series of those signals. Delta n minus k is just a delta function. Here it's a 1. This is a discrete time delta function. So delta n minus k equals to 1 when n equal to k, equals to 0 elsewhere.
Read the rock wall.
And then you sum everything together, it gives you 1. Versus if in the continuous time domain, delta t, remember that, right? Delta t is actually equal to a infinite when t equal to 0 or t equal to and a 0 elsewhere. And then what we need is we do the integration delta t dt to calculate the area. That is 1. Okay, just a little bit different. So if you look into the discrete time domain, it just because it's all discrete, I have just one sample. You sum up everything, it's just 1. So what we do is we just extract the signal here. If we multiply these two signals, so we extract, this is my xk delta n minus k. So it's very simple. We are doing a sampling. I'm just picking up each one of those samples, and then you add them together. Of course, it gives me the original signal xn. Now let's look at the response of the system to an input signal. First, we define the response of a very simple input, which is my delta function. Suppose I have a delta n subtract k. Remember, it's just one spike, right? In time, it's at one particular time, I have a 1 coming. Going through my system, and I have the output. The output here is, let me call this y. This output is called h. H is the output when the input is a delta function. So the delta function goes through my this operation and give me h. It's a function of time, of course. Time index is n. And also we have this delay of k, or the time lag of k. So I also have this relative time index of k. So it's a function of n and k. We define that and we call h is the impulse response. H is the impulse response because it is the response of an impulse function. If I have an impulse, I have a response of the impulse. So this is h, the output. Again, this output is h. how can we use this H to describe, actually, we indicate the entire system here. This is my linear time invariant system. We use this sum to represent my any input, arbitrary input signals, xn. Xn is we're counting one sample after another. So it's summation of xk, each sample at time k, times delta n minus k. Yn is the operator t on the xn. Xn is input function. And then the last slides we show that we can do this because t is a linear operation. So we put this t inside and then working on each of the input. Each of the input here is this. Now xk is a constant. You can pull this out of, you can think that as a weight. So pull this out of this operation. And the operation is really working on this signal. Signal is in terms of, that's a signal function of n. Right? And because I defined the impulse response, therefore this part can be represented using this impulse response. That's my h as a function of n and k. Now we need to use the second properties of linear time invariant system. Linear time invariant, all we used here is a linear property. So if it's a linear system, the operation can work on each individual inputs. And then I have individual outputs, add them together, give me the combined output. Time invariant, the second term is time invariant. That is saying that if I have the operation on delta n, give me hn, then if I have the operation on delta n minus k, I will have an output which is hn minus k. It only matters the relative time. Only the relative time matters, n minus k. So I have a time index n, I have a delay index k, but the relative time n minus k, I only care about that. So with that signal y, output signal yn, and here from here, and then replace this term by this term. So that's hn minus k. Okay, so that is a so-called a convolution sum. So that's the discrete time convolution. Convolution is yn equals to xn convolved with hn. Convolution from the discretized, from the analog or the continuous time, we know convolution is something that we take the, if this is a t, and then we have another term is tau, tau and t, subtract tau d tau, and we got y t, right? So in discretized, in discrete times field that we have yn equal to the summation of xk times hn minus k, and that is the sum, convolution sum. Okay. Rewrite this convolution sum here. We have here this yn equal to xn convolved with hn. It is this convolutional sum. Convolutional sum, I can mathematically, I can change the h and the x, the first one using hk times xn minus k, and sum together, that will be the same. You just change this variable, this summation variable, and that is equal to hn convolved with xn. So first we know that I have a system. If the system is linear time invariant, I can represent the system using hn. Hn is that now from the original definition, hn is if I have the delta n as my input, this is the impulse response. Therefore, what I have here, of course, by definition, it should give me hn. That's the impulse response. The last slides, we show that if I can have a xn and an arbitrary signal as input, going through this linear time invariant system, and then I have the output yn should be exactly equal to xn convolved with this Hn. And we are using Hn here to indicate the entire system. It's called impulse response. So any arbitrary input convolve with the impulse response and give me the desired output. Because of this and this, they are equal. We can have the picture like if the input signal Xn going through the system indicated by impulse response, give me Yn. I can also think that as something is our Hn coming into this linear time invariant system described by Xn, also give me Yn. So this block diagram indicate a convolution. It's important to understand the convolution. A convolution, if I have a linear time invariant system, it can be indicated by a convolution. That's it. It can be mathematically expressed as a convolution, as we used last time, Yn equal to the input Xn convolved with the impulse response Hn. So let's look at some properties of this system that is represented by convolution. Identity and shifting properties. So the identity properties of this convolution is that if I have a signal Xn convolved with the delta function or delta n, then I have the output is Xn, identity. And we did that before, which is Hn convolved with delta n equals to Hn. We also have this shifting property, Yn subtract k, that is equal to Xn convolved with delta n minus k. So we shift it. That's equal to, because the property of delta function. So we are going to pick up the signal x exactly on time n equal to k. So we have Xn minus k. We take this out. Commutative law, we show that from the convolution identity equations. Xn convolved with Xn equal to Xn convolved with Hn. Associative law, Xn convolved with H1n convolved with H2n. I can associate the later two terms together first, H1 convolved with H2, then convolved with Hn. So what we have here is, if I have a system drawing this block diagram, that's the same as I going through a combined system Hn, that is H1 convolved with Hn. And I can also understand that we have the similar effect if the signal go through those two parts. The signal if go through the second system first, H2n, and then go through the first system, H1n, that's the same, because of this commutative law and associative law of convolution. And therefore, if we know if we can do that, we change the order of those two systems, that prove that the convolution is indeed a linear operation. The distributive law. So the convolution, it looks like a multiplication. So Xn convolved with H1n plus H2n equals to Xn convolved with H1n plus Hn convolved with H2n. From a block diagram, that means that if I have those two systems working in parallel, H1n and H2n, I can think the entire thing as a big system equals to H1 plus H2. And then I have my input signal going through that combined system. So we know we are interested in the linear time invariant system. Linear time invariant system can be represented by a convolution. And with that, we can do many work for the analysis of signals and systems. Look at some special case. One special case is called the causal linear time invariant system. Now, causal system, by its physical definition, it is a system, the output only depending on the current input and the previous input. It does not depend on future input. Let's look at mathematically, what does this come out? I'll have my output, Yn, yn0, my current time is n0, yn0, that is equal to this convolutional sum. That's yk times x n0 minus k. And we sum that together, k from negative infinite to infinite. Break that into two terms. The first sum, when k is non-negative from 0 to infinity. The second term, when k is a negative integer from negative infinite to negative 1. So the second part, y tilde, depends on the input. Let's see, those input are xn 0 plus 1. K is negative 1. Xn 0 plus 2 all the way to xn 0 plus infinity. And these are the future inputs, right? Future with my time n0, future inputs. Now you said that if I have a causal system, the causal system should not depend on the future input. Therefore, I should make this h all zeros. If I have all these h all zeros, then indeed my system does not depend on future inputs. And these are the h when k is negative, right? Therefore, the impulse response of the system, hn impulse response completely describe the system, must satisfy the condition hn equal to 0 when n less than 0, when the time index for this impulse response is negative. And then I have this part. These parts should be all zeroed to make my system causal. Therefore, just to remember, this is a mathematical form to describe a causal system using the impulse response. Okay, write out this again. If I have a causal linear time invariant system, that means my impulse response hn equal to 0 when n is negative. And then the convolutional sum can be right. This is one-sided convolutional sum. K from 0 to infinity. Or if we're putting x first, xk, hn minus k, then k equals to negative infinity to n. The second property we know is the stability of a system. Stability of a system, we have a BIBO, bounded input, bounded output stability. If xn is bounded, if xn, each xn input is a finite number. If yn is bounded, that means each output y is finite, is less than or equal to capital Ym. Let's see what are the conditions on my impulse response when I encounter a BIBO stable system. Using the convolutional sum to indicate my system, this is convolutional sum. Now I only care about the magnitude or the absolute value of y. So I'm taking this absolute value of y equal to the absolute value of this combined this sum. And then it is less than or equal to, I put the absolute value inside the sum. So the absolute value from here to here. Then I can break that into two. So the absolute value of hk and another absolute value of x n minus k. Right? Because the absolute value inside the summation, so you expand that. So less than or equal to that. And we know the input xn, input is finite. Therefore, this entire thing is less than or equal to mx. We take this, each one is smaller than mx. We take the constant out of the summation, mx times sum over absolute value hk, k from negative infinite to infinite. So less than or equal to that. And we are using less than or equal to, same direction. So it's okay. I can write this down, those expressions. So we observe that for my output yn to be finite, a sufficient condition is that I need to have this term, which is the sum of all these absolute value h's less than or equal to less than infinity. It's finite. So if we look at here, so it means that, right? If this is finite multiplied by constant, then the entire thing is finite. That's what I want. I want to make sure this is true. So sufficient condition is that I need to have this term, this sum is finite. It turns out this condition in the box is not only sufficient, but also necessary to ensure that the stability of the system. It is indeed an if and only if condition. So we are not going to prove the second necessary part. We are using this formula in the box to check if my system is stable or not. A linear time-invariant system is stable if and only if its impulse response is absolutely summable. How do you check a stable LTI system? You say, well, I can look into its impulse response of Hn, and if Hn satisfy this absolutely summable equation, satisfying this condition, and then I have a stable system. Put these two together. I have a causal system, and I also have a stable system. Now, for causal system, we also have another more restricted situation is I have a finite duration impulse response. FIR system has an impulse response that is 0 outside some finite time interval. So remember the first term, this part is causal system, right? And then also, if n is greater than an integer time, capital M, it's also, we have Hn equal to 0. So what does that say? Is that say, if I have, this is time n, I got H0, maybe H1, we have a H2, I may have a negative term, H3, H4. It says that I have a finite support. So beyond the range of 0 to m, this m is, this is for actually m is here is 5. Okay, this is m as definition here. So beyond this support, all the h's are zeros. Beyond that, all the h's are zeros. So I have an impulse response has a finite duration, in this case from 0 all the way to 4, all the way to n-1, a finite duration. And that is called the FIR system, finite duration impulse response system. Then the convolutional sum can be written in this form. It's still the same product and we sum together, but the summation k is from 0 to n-1. It is a finite duration. On the other hand, an infinite duration impulse response has an infinite duration impulse, IIR system has an infinite duration impulse response. So we have that. The only difference is that the k goes to infinity. From 0 to infinity, it's starting from 0 because I still want a causal system. In practice, every system is causal. So I have a causal system, and then the summation is from 0 to infinity, where the causality is assumed. Before I close for today, I want to ask a question. I wonder why this impulse response Hn is so important. All we have here is to understand that here's my system, a linear time-invariant system, input xn, output yn. And we said the linear time-invariant system is using this Hn, the impulse response, to represent that. And the way we can do that is because it's a linear time-invariant. And because that, we have a convolution, xn, convolved with Hn, equals to Hn convolved with xn. Hn is impulse response. Therefore, if my input is delta function and the output is Hn, it is the response of an impulse. So Hn equal to delta n convolved with Hn. My system is still Hn, so it's Hn convolved with delta n. That is using the identity properties of delta function. Now my question is that, why this HN is so important? So we can actually using HN to include all the properties or to describe completely the system. As we can see here, I'm checking on the HN to see if my system is causal or not. I'm checking on HN to see if my system is stable. So it's kind of independent of the input signal, output signal, X and Y. I'm only looking at HN, and HN should completely describe my system. Why is that? Let me give you a hint. Now, what is HN? HN is something you observed when you excite your system with an impulse. Okay. How to know the properties of the system? Well, I need to try a lot of inputs. I need to try maybe many different input Xn. But in this case, I choose the input as an impulse. It's just a one excitation at a certain time. It's very short, but it's powerful. It has some energy coming in. Go through the system. I measure the output. The output is Hn, and then that Hn completely describes the system. Delta function is such a good testing signal. If I look at it from the frequency domain perspective, right, what is the frequency response of delta n? Fourier transform. Later we will see the mathematical Fourier transform. If we transform that into the frequency domain, what we have a constant, which means here's time. In time domain, I have a spike. This is my delta n. It's Fourier transform. In the frequency domain, I have everything across the frequency span. I have everything. For Fourier transform, it's a constant 1. Therefore, indeed, I'm testing the system using all the frequency inputs. And then I know what are the response to all the frequency inputs. And then, of course, I know the entire thing of the system. That's why the delta function is so important. It's just a spike. It's excitation, but it covers the entire frequency. Okay. Now, to conclude that, Hn, the impulse response, is indeed one of the key measures of my system. It has to be a linear time invariant system. It tells me about everything about the system, how to relate input and output, and that is a convolution. Output equals to the input convolved with this impulse response Hn.